Welcome students, in this lecture we shall prove that under the root 2 is an irrational number. This is our first lecture on real analysis. If you want to watch my other videos on real analysis, you may visit playlist or description. We will prove this result by contradiction method. First we assume that under the root 2 is a rational number, then we will try to bring a contradiction. So assume that under the root 2 is a rational number. Let under the root 2 is rational, and we know that every rational number can be expressed in the form p by q, that is under the root 2 is equal to p by q, where p and q belongs to set of integers. We also assume that GCD of p and q is 1. This means that this fraction is in its simplest form. For example, if we have a fraction 2 by 4, this is not in simplest form. We can write it as an 2 by 4 equal to 1 by 2. So this fraction is in simplest form. Here GCD of 1 and 2 is equal to 1. There is no common factor between 1 and 2. Now if we take square of this equation on both sides, we get 2 is equal to p square upon q square. This is our equation number 1. We will also use this result, that GCD of p and q is 1. Now from this expression we can write 2q square equal to p square. Now p square is equal to 2k square. From here we can write 2 divides p square and q square also divides p square. But we just take this expression that 2 divides p square, because if we write a number as 8 is equal to 2 into 4, then 2 divides 8, also 4 divides 8. But we take just this expression that 2 divides p square. Now look at the number which are divided by 2. Look at the integers or square of integers which are divided by 2. So 2 divides 2, 2 divides 4, 2 divides 6, 8, 10, 12, 14 and 16. Among these even numbers, we choose the numbers which are square of an integer. 4 is square of an integer. Similarly, 16 is square of an integer. No other number is square of an integer. Now 2 divides 4, and 4 is equal to 2 square, and 2 divides 16, and 16 is equal to 4 square. Now if 2 divides square of an integer, then 2 must divide that integer, then we can write as 2 divides 2, and from here we can write 2 divides 4. Now by using this concept we can write 2 divides p. If 2 divides square of an integer, then 2 must divide that integer. From here we can write p is equal to 2 into some integer, say m. This is our equation number 2. Now we use this equation 2 in equation number 1. So equation 1 implies As 2 is equal to p square upon q square, we can write as 2 is equal to 2m square upon 2m square upon q square since using or putting p equal to 2m in equation number 1. From here we can write 2 is equal to 4m square upon q square. After cancellation we get 1 equal to 2m square upon q square, and from this expression we can write as q square is equal to 2m square. Q square is equal to 2m square. Now by using same logic, as we used above, as q square equal to 2m square, which implies 2 divides q square and m square divides q square, but we choose this expression that 2 divides q square. When 2 divides q square and q is an integer, by using this logic again, we can write as 2 divides q. Now 2 divides p, we have two expressions. First one is 2 divides p, this is our equation number, suppose A, and we just proved that 2 divides q, this is our expression p. So by using these two expressions from A and B, from equation A and B, we can write 2 divides p and 2 divides q. This is our contradiction because we assume that GCD of p and q is 1. Here we assume that GCD of p and q is 1, means there is no common factor between p and q, but here we prove that 2 divides p and 2 divides q, which is a contradiction. This is our contradiction because GCD of p and q is 1. So here we assume that, first we assume that GCD of p and q is 1, there is no common factor between p and q, but here we assume that p and 2 divides p and 2 divides q, which is a contradiction. So this contradiction arises due to our wrong supposition, and our wrong supposition is that we assume that under the root 2 is irrational number. This is not true, which implies this contradiction arises due to our wrong supposition, which implies under the root 2 is an irrational number. Hence proved. Thank you very much for watching this video lecture.